Today we're going to talk about something that's called the Pythagorean theorem. Most of you will probably have already heard of this at some point in algebra or previous math class, but we are going to discuss this again in terms of some geometry. So the Pythagorean theorem says in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. We tend to think about this in a formula. So if I draw a picture of a right triangle, it says in a right triangle, then in that right triangle, I'm going to label the legs A and B. It doesn't matter which is which, but I'm going to label the hypotenuse C, and that's important. The hypotenuse always needs to be C. It says the square of the hypotenuse. So since the hypotenuse is C, I'm going to call it C squared. The square of the hypotenuse is equal to the sum means that we're adding, the squares of the legs. A squared, B squared. Okay? So A squared plus B squared equals C squared is our Pythagorean theorem in formula. However, if I ask students to state the Pythagorean theorem, they usually say A squared plus B squared equals C squared. It's not 100% right because we forget an important detail then, that this is only true in a right triangle. When students learn the Pythagorean theorem, they tend to make it a little bit more broad than it is. It's a really important theorem and a really important rule, but it only works in a right triangle because it talks about a hypotenuse. And only a right triangle has a hypotenuse. So a lot of times when students learn this, they start doing this to any triangle they see. Okay? It only specifically works in a right triangle. It's also important that it says the square of the hypotenuse is equal to. We need to make sure that we're always labeling our hypotenuse, that's C. That hypotenuse has to be the one that's all alone in the equation. That's the most common mistake that students make in solving problems with the Pythagorean theorem. You need to make sure that the hypotenuse is the one that's C, that's all by itself in the formula. This formula came about a long time ago. Ancient Greece, there was a group of people that called themselves the Pythagoreans. There was actually a person named Pythagoras. It's not necessarily believed that he himself came up with this idea. Probably even existed before the group of the Pythagoreans. But they really studied this and did a lot of work with it and kind of made it their thing. The Pythagoreans believed that math was like higher than anything else. They were not a Christian group per se because they believed that math was really the thing. They, however, tended to think of this as more. They tended to think of this as more of a geometric idea than an algebraic idea. So in our culture, we tend to think of Pythagorean theorem, A squared plus B squared equals C squared. We're very algebraic about it and very formulaic about it. They thought about it more in a geometry sense. So that what they would do is say, if I have a right triangle, I can draw a square on each of those sides. So if I draw a square on one of the legs, so that side had a length of 3 on the triangle, so I made a square of sides 3. I can draw a square on the other one. It had lengths 4, so I can draw a square of 4 there. Then I can draw a square on the hypotenuse. It's a little bit trickier because I don't get to follow lines, so we're just going to pretend like what I draw is actually a square. They said that the area of those two squares that are on the legs should be exactly the same as the area as that square that we drew on the hypotenuse. So the ones on the legs, we can easily count up the area because we can count the little squares in there. And see that the lower one has 9 in it, the side one has 16 in it, so I put together the 9 and the 16 and that gives me 25. That means that there should be 25 squares inside of that other one. Now it's harder to count them up because some of them along the edges are chopped up and they make little parts of squares. But if we could actually cut them all out and piece them together, there should be 25 squares of area in that space. Okay? That's the way that they actually thought about this theorem more. was to say the square on each of the legs added together gives the square on the hypotenuse. When we hear the word square, we think of it much more algebraically. It works that way, but this was how their thought process kind of worked in it. We are done with proofs. But the Pythagorean theorem is an interesting theorem because it has been proven more than any other theorem. And I mean, like, newly proven more than any other theorem. We can prove a theorem in class, but we didn't really prove it because somebody else proved it before, right? So when I say it's been proven more than any other theorem, that means like a brand new way of thinking about it. Literally hundreds of different proofs for the Pythagorean theorem exist. Some of them very algebraic, some of them very geometric. One of our presidents actually proved it, President Garfield. I know nothing else about him because I'm not a history person, but I do know he proved the Pythagorean theorem in a brand new way that had never been done before. So this theorem is really interesting to think about proof because there's so many different ways of thinking about it. Okay, so some examples that will be similar to what you'll see in your homework. First, we need to talk about, again, just a little review of how do we square numbers. Because if we're doing a squared plus b squared equals c squared, we're going to be doing a lot of squaring. So we want to make sure we know how to appropriately square numbers. So if I have the square root of 5 and I square it, what do I get? When we square a square root, they cancel because that's opposites. It's like multiplying by something and then dividing by the same exact thing. You get right back where you started. A square and a square root undo each other to just give us whatever was underneath there. So when you square a square root, you just get the number that was in there. When we square a number that has an integer part and a root part, we talked a little bit about this when we went over the homework problems. We need to square both the integer part and the root part. So I need to square the 7 and get 49, and I need to square the root part, and that, like the last problem, would just give me a 2. When we square a root, we just get what was underneath it. We're multiplying those together to then get 98. Okay. So when you square a number that has more than one part to it, we square both the number out front and square the root, and then multiply them together. When you square a fraction, what would we get? Nine over 5. Square the number and square the root, and they stay wherever they are in the fraction. So squaring the 3 on the top gives a 9. Squaring the root that's on the bottom gives just whatever was underneath it. Okay? So when you square a number that has more than one piece to it, just square all of the pieces. Okay, so then some problems for how we would apply the Pythagorean theorem. You'll be given a right triangle and 2 pieces of it, looking for another piece of it. The most common mistake that students make with the Pythagorean theorem is doing number you're given squared plus number you're given squared equals number you're looking for squared. Okay? That is not what the Pythagorean theorem says. The Pythagorean theorem says the sum of the squares of the legs equals the square of the hypotenuse. It means the hypotenuse always has to be by itself. Okay, so what we are looking for is not necessarily what we put by itself. The hypotenuse is what we put by itself. So what's the hypotenuse here? 10. Remember, hypotenuse is across from the right angle. The hypotenuse must be the one that's by itself in the equation. So we'll have 10 squared equals x squared plus 7 squared. It doesn't matter what order that x and 7 go in because we're adding, and 1 plus 2 is the same as 2 plus 1. So that doesn't matter. But what really, really, really does matter is that the hypotenuse is the one that's all by itself. Okay. Then we're going to square our numbers. 100, 49. I'm trying to solve for x. So I'm going to subtract the 49 from both sides. But I don't want to know what x squared is. I want to know what x is. So how do I undo a square?
Square root.
Square root. Squares and square roots are opposites. They undo each other. So I'm going to square root both sides of this, and that will give me just an x. And the square root of 51. No decimals. Okay, so don't just type that in your calculator. Either leave it as it is or simplify it if it is possible to simplify it. So when we simplify, we're looking for a perfect square that goes in there. So 4 doesn't go into 51. 9 does not go into 51. 16 does not go into 51. 25 does not go into 51. 36 does not go into 51. 49 does not go into 51. And we're done. So square root of 51 just stays what it is because nothing goes in there that we can take a square root of. But you want to check through that list of perfect squares and see if it can be simplified. If it can be, it should be. But no decimals.
Since we have to end up square rooting anyways, why don't we just square root at the beginning just to have 10 equals x plus 7?
Because that's not true. Because that would give an answer of 3, and 3 is not the square root of 51. You can't just take square roots of parts of a sum. It doesn't work. It's order of operations thing. Next example. Which of those is the hypotenuse? Yes. So that's the one that's going to go by itself. X squared gets to go by itself this time. Equals 4 squared plus 6 squared. Always make sure your hypotenuse is alone. Then we square the numbers we can square. So 4 squared is 16 and 6 squared is 36. Since they're on the same side, we can just add them up. 16 plus 36 is 52. And we said in the last problem, to undo a square, we do a square root. Gives me x. And then we need to think about simplifying. Are there any perfect squares that go into 52? 4. 4 times 13 is 52. So we need to simplify our square roots the way that we learned a couple days ago. Square root of 4 is 2. So we get 2 square roots of 13. Simplified roots as answers when possible. No decimals. Questions? One more example for you. Whoops. Which side of this is the hypotenuse? 2x. So that's the one that has to go by itself. So now I have 2x all squared equals x squared and 5 squared of 3 all squared. When a number or a side has more than one part to it, we want to make sure we square that whole thing. So what is 2x all squared? Four x squared. We square the number, 2 squared is 4, and square the x squared. Okay, when a number has more than one part to it, make sure you square all the parts. Square the 2 and square the x. So when we square this 5 squared of 3, we need to do that same thing. Square the whole thing. Square the 5, and I get 25. Square the square root of 3, and I get 3.
Well, yeah, square root.
And then that's 75. Okay? Square the number in the front, gives me 25. Squaring a root cancels the root.
Oh, no.
So I just get a 3. Multiply that together, gives me the 75. Trying to solve for x. What do I do next to this?
You subtract x squared from both sides.
We want to collect all the x's together. Right now they're kind of spread out on different sides of the equation, so we want to get them all together. So I'm going to subtract an x squared. 4x squared minus x squared is 3x squared. Then what? And divide by 3. X squared is 25. And then we would square root. And I get x equals 5 because square root of 25 is a nice number. Questions? All right, your assignment is from 8.2 tonight.